Welcome back to the today's class. Today we will be seeing about field effect transistors. It is shortly known as FET devices. So the field effect transistors are being used to switch on and switch off electronic devices. It is classified into two types. One is JFET, which is nothing but junction field effect transistors, and another one is MOSFET. It is metal oxide field effect transistors. So both the FET devices will classify based in the transistor. So here the JFET is a current operated device, whereas the MOSFET is a voltage operated device. So the operation principle for JFET is very similar to as of a NPN transistor and PNP transistor. Similarly, for the MOSFET, the supply given to the MOSFET in the gate region, so the applied voltage will be proportional to the output voltage from the MOSFET. This causes the MOSFET to be a voltage control device and JFET to be a current control device. In JFET you are having two types. One is N channel JFET, other one is P channel JFET. First we will be see about N channel JFET. In N channel JFET has the major portion covered by N channel. So this is the top view of the JFET. Here the N channel present here will be the major portion of the occupied region, whereas the P channel present here will be a small portion embedded in the N channel, so that the FET devices can work. So there are three terminals in a JFET. They are source, drain and gate. So the source is the pin where you have to supply the voltage, and drain is the pin where you have to get the output from the source. Usually drain is being connected to the ground, and the gate provides the signal to turn on and turn off the JFET. So working of N channel JFETs. So in case 1, no voltage is applied to the device VDS, that is the voltage across drain and source, and similarly the voltage across gate and source is 0 volt, which represents the voltage across drain and source, and gate and source is 0. In this state the device is ideal. No current flows through the device. So the current through the source to drain IDS is equivalent to 0. N channel JFET working. Case 2. The supply is applied to the VDS terminal of the JFET. Here this is the circuit diagram. Here the supply voltage, which is the VDD, which is being applied into the load resistance, and it is being connected into the drain and source terminal of the JFET. And similarly the gate terminal of the JFET is directly grounded, which represents the gate voltage, that is the VGS voltage is 0. Since the gate voltage across the JFET is 0, the JFET is said to be in the off state and no current flows through the device. So IDS is equivalent to 0. So since the applied voltage into the gate is 0 volt, the current ID cannot flow into the JFET, so the load cannot be turned on. Similarly in the case 3, the supply voltage is applied to the VDS terminal of the JFET, and the gate voltage is applied to VGS is positive. So in this case you may see the battery is being connected across the gate, so that the voltage is being applied to the gate terminal of the JFET. This causes the current ID to flow into the resistance and into the device. So this causes the FET becomes in turned on position. In this state the JFET is said to be in on state and current IDS flows through the device. So this is the characteristics graph of a N-channel JFET. Here the x-axis represents the drain source voltage and the y-axis represents the drain current in milliamperes. So once it is being plotted by varying the drain source voltage, which represents the voltage across the drain and the source. This voltage is being varied with the help of the potentiometer which is connected here, and the drain current is being measured. Once you change these voltages, the current and the voltages which are being applied gets varied. So the main characteristics here is the voltage across the VGS terminal decides the amount of drain current. So if you apply a gate source current, so that is the gate source voltage of -4 volt, then the drain current will be of 1 volt. So if you take it as -3 volt, it comes up to a level of 2 volt, and if you give the gate source voltage to be -2 volt, it will be of 4 volt. So by varying the gate source voltage, the drain current present here can be increased. Next we are moving into P-channel JFET. P-channel JFET has the three major portions covered by P-channel. Here this is the substrate. Here the substrate P will be having the major portion when compared with the N. So the substrate, in this P substrate, you may see the N substrate is being embedded. So this causes the P-channel JFET. So the symbol for the P-channel JFET is source, drain and gate. The arrow which is in the state it is going out from the gate represent it as a P-channel JFET, whereas the arrow which represents entering into the gate represents N-channel JFET. In the working of P-channel JFETs, first consider the case 1. Here this is the P-channel JFET, which is represented by the arrowhead which is entering out from the gate. Here the drain source voltage is 0 and the gate source voltage is also 0. This represents that the device is in off state or it is in ideal state. So this causes the drain current, that is the current from the drain to source, is also 0. In case 2, the supply is applied to the VDS terminal of the JFET. So the gate voltage across the JFET is 0. In this state, JFET is said to be in off state and no current flows through the device, so IDS is 0. So in this condition, you may see the applied voltage across the gate and the source terminal becomes 0, but there is a voltage across the drain and source. This causes the current to flow since the gate voltage is 0. The current cannot flow through the drain and source terminal of the JFET. In the third case, you may see the applied voltage across the drain and source terminal is present across the JFET, and the gate voltage is VGS is a negative, and so the characteristics of the device is represent here. So the drain source voltage is of -volt, so you are going in the negative region, and the drain current is given. Similarly, the gate and the source voltage is being of +volt, irrespective that you have connected the multimeter in the reverse direction. So the gate source voltage, if you go on increasing the gate source decreasing the gate source voltage, the current present in the drain goes on increasing. So above the ohmic region you are having a saturation region. After the saturation region, if you go on increasing the VDS voltage, the breakdown will occur. Thank you.